Oh, thank you very much for attending my talk. I want to talk about these topics, and there are three things I want to talk. I'll take one by one. I was in Tokyo Tech, and at that time, maybe it's about 150 robots I made. And now I am a director of a hyper environmental robot laboratory. I call it the Hero Lab. It is a kind of group company of a Tokyo Electric Power Company, TEPCO. So we are focusing on the development of a decommissioning robot. For example, long reach, high payload, telescopic rod. It can extend to 2 meters to 50 meters, and very slender, and still it can support 10 to 20 kilogram weight. Also, we're studying of a universal mobile robot on the ground, also on inside the shallow waters. But this time I cannot go into detail about the decommissioning robot. And the audience may be specialty is different, so I would like to discuss some kind of mundane topics. Just 2 years ago, I commute to my laboratory by bike. And when I wear the mask, it is very, I feel very bad. So I wanted to make something which makes mask breathing easier. As you know, the mask covers your nose and mouth. So exhaling air remains inside the mask. So if you inhale, the remained exhaled air go into the nose, and it's not so good. So what I wanted to do is to divide the space inside the mask up and down, and put some check valve. And the air from the nose should go downward, but not go back. And at that time, I also made a lot of models. I counted for several months. I made more than 10 masks, thinking about many aspects. Of course, one of the biggest problems is airflow. This one is the check valve I developed. It works well, but still the resistance of air is a little bit noisome. This one is with a turbine, okay? And every time if you exhale, the turbine rotates, and it moves 1 second. So the air is always go downward. So it works well, but the problem is the sound. The rotating sound are slightly hard. So it's very difficult to reduce the sound. So I thought it might be a good idea to sell by the name of Darth Vader in a mask. Okay, but of course it wouldn't sell well. So I tried to improve, and finally I found that only the hole is enough. We don't need any valve or turbine. And now it is selling from the Amazon. There's only a hole, and another one is a hook around it to stick to the inner surface of the mask. The hole is not round, but upper one is a hexagon, and the lower one is a square to stop at a certain position. And well, I can, if you are interested, you can get this mask at the Hero Lab booth, free of charge. So if you are interested, go there and get one and try it. Anyway, while I'm making this model, I start to wonder why we inhale from the nose and exhale the nose. Okay? Why we use the same path? In the case of zero brazing, the water enters from the mouth and goes back. So it's one-way flow. So inhale and exhale air or water wouldn't mix. But in the case of our breathing, it's always a danger to mix. Okay. So I studied about physics documents and found that land animal try to make the body organ wet. Okay, so maybe if inhaled air is passing through the trachea, or inhaled air alone, it will dry the trachea. So maybe landmine evolved to pass the inhaled air through the same trachea of the exhale. For the exhale trachea is always maintained wet. Okay. But as I said before, the air mix. So they also evolved the nostril very narrow. Okay. So, and if the narrow, the exhale air goes far from the nose, and inhale air is from the nose. Okay. This one's a simulation of the airflow. Inhale air is no velocity at all. So it's always around the nose, but exhale air goes outside. So by this mechanism, just making the nose small, they developed to separate the inhaled and exhaled air. So I found, I didn't understand why only the nose is enough, but I found that the whole of the hero inner mask only to help the natural separation mechanism of a nostril. Okay, that's one finding. So making it's a very simple making, but that is lead to our kind of scientific solutions, scientific discoveries. Well, this one is my first study when I was in Tokyo Tech. I bought a real snake and let it move on artificial lawn. And after that, I decided to make a snake-like robot. In 1972, I made this model. It's about 2 meters long, 20 segments, and it moves exactly same undulation motion of the snake. The problem is what kind of curvature should be supplied. Of course, most natural undulation is a sinusoidal movement. So at that time, there are no computers, so I made an analog circuit, and we supplied from a function generator, we supplied the undulation motion to the front segment, and that signal is shifted to a certain delay to the backward. Like bucket relay transmission. And I thought, of course, sinusoidal signal is the best. And as a result, I generated a curve which curvature is changing along sinusoidally along the curve. And at that time, I tried to find out the name of this curve by consulting many mathematical dictionaries, but I couldn't find it, so I named it serpenoid curve. And I found it's very closely related to the real snake. And even the flagella curve is very similar to this wave. And I bought the book in Japanese and also in English. It's 1994. I forgot about this that time, but in 1996, I got the mail, paper mail at the time, from the Emeritus Professor of UC Berkeley, Professor Luna Leopold. I found he is a pioneer researcher of the flow of the river. And he said, in his book, there are many examples, but he said that mechanical expression of the meandering of the river is exactly same as a serpenoid curve. And they call it sign-generated curve in civil engineering. I don't think at all to study the civil engineering textbook, so I couldn't find it. But so he explained that the effect causing the undulation of the river changes sinusoidally along the river. That's why it makes the same curve of serpenoid curve. And this one, this serpenoid curve is used all the snake-like robot that I made afterward. This is amphibious snake-like robot, and it transmits sideways and up and down sinusoidal motion. Okay, so this is one thing, and afterward I want to study about the controlling problem of the snake to grasp the object, arbitrary shaped object. And I try to add the tactile sensor on both sides of the body, and when the pressure applied, what kind of shape the snake bent. And of course, if the only one point is pushed and that part only bent, all other parts bent, so it's not so good. So what I thought best is to bend that one and also bend adjacent joint to the opposite direction, like this. And this is experiment doing that. There's a limit switch on both sides, and there's a small wheel to make it smooth to rotate. And all the segment have the same control. So by this way, it automatically coiled around the object. And this one is another experiment. We supply, the wiring was very, it takes a lot of time to do all the wiring. But anyhow, all the joints is under this control, and it can coil around the object like this. これスキップできないのかなOkay, so they don't no, we don't give any command of the posture, only to follow the motion under the tactile signal. But it automatically goes around the arbitrary shaped object. Okay, let's keep it. And the same control is applied to drive the snake robot inside the labyrinth. Every time it hit the wall bent to follow the shape. And that bending motion is shifted to the rear direction, and it automatically moves inside the labyrinth. The caster under the snake robot is free casters. So all the propulsive force is come from the wall. Okay. And what I did is this control. And if we're thinking about the joint supplies with a hose, it gives a signal from both sides as a negative signal. So we can express like right side. And by changing the equation, it becomes a very similar, very acquainted, well-known form. And it is a second derivative. So I found that what I did is to derive the snake robot of the second derivative of the pressure. Okay. So, and afterward, I found that this kind of control method is very widely observed in a nervous system. And it is called lateral inhibition. It always gives the inhibitional signal to the lateral direction. And lateral inhibition is one which differentiate the input signal. Okay. So our sensors are very sensitive to the differential of the input signal. For example, if you see this object for a while and close your eye, and you find peripheral, the bright white line. Okay. It's because the lateral inhibitional processing is down. So it's always it's a differentiation of the input signal. So the H is always emphasized. And from this, I don't do anything at all. It's only my assumption, but I think that the protozoa, a very beginning animal, has a very slender body, and it's moving inside the ocean. Maybe it try to enter its narrow hole, and when it's going to narrow hole, as I showed before, the lateral inhibitional control is very effective. So maybe they acquired such kind of neural network. And tactile sensing is a fundamental of all the sensors. Vision or acoustic, all our sensors is very sensitive to the differential of the input signal. Maybe that, I thought we can explain why we acquired such kind of sensing features. Maybe it comes from this kind of motion. So making snake-like robot, of course, it leads to some practical things, but it's also connected to science discovery. One is a serpenoid curve. This curve is very ubiquitous, not only for the animal locomotion, but also the river flow. And lateral inhibition is another thing. And I also want to make more practical snake-like robot which can grasp the object softly. In the case of the strength of material, if the cantilever beam is supplied uniform pressure, the bending moment diagram is a parabolic, as shown at the left side. So if you change the causality, and if you supply the parabolic bending moment, it will generate uniform pressure. Based on this idea, I make this model. The diameter of the pulley is changing parabolically. Okay. It's free to rotate, but still it generates a torque. And based on this idea, I made this model. If we make it, we will use a 3D printer, but still it takes only a week. And I make the first the gripper which grasp the object softly. Yellow one is for the opposite direction to release, and there is a two double pulley So from the base, it round the big one and the small one, and it goes outside, big one and small one. So it decreases parabolically. So just pulling the wire, it can coil around the object of the arbitrary shape. Well, I skip again. Okay, so I found, afterward, I found that what I did, the soft grip mechanism is one of the differential mechanism. Until now, until that time, there's several differential mechanisms proposed, just like a bevel gears one or Plenary gear. But I found this mechanism can be included, that mechanism. And if the differential mechanism, it has a three port, which moves the energy. And one port is connected, I call it connected differential mechanism. The input signal is distributed to many segments. And that's what I did. And it was, I bought the paper in 1978 for this device. And just recently, 2017, I got an award that it is selected top 10 most cited paper in the publication of machine and mechanism machine theory. So it started from a very simple machine. It took only a week, but that can be connected to the finding of the underactuated hands. By the way, this is the second model I discussed with firefighters, and they need the gripper to grasp the human body. So I did several experiments. I did the experiment with a student, but it's not so interesting. So I made experiment by using this charming lady. And after this careful experiment, she became my wife. Okay. Okay, next is non-verbal thinking. For this, I want to show the psychological experiment. The German psychologist named Karl Duncker made a very interesting experiment. He provided weight, string, and nail. But group A, he provided separately. But group B, he connected the string to the weight. Okay, and all the students of group A hit the nail on the wall by using the weight. And most of the students of group B did that. But some of the students, some of the students said, it's impossible, for we are not provided hammer. Okay. I think when the weight and the thread is connected, these students said it is a pendulum. Pendulum cannot be a hammer. So because they thought by the name, they limited the way of using the object. This one is just a month ago. My gripper of the bicycle was broken, so I wanted to insert the new grip. It's made of rubber. And the experiment says that the instruction shows that we should use compressed air and make it bigger and insert. But I don't have a compressed air at home. So what I did is to use a glue. Glue is a lubricant when it is out of the tube. So I painted the glue and make it smooth and insert and left it 1 day later, it is fixed. It is a very easy way to insert. Now in Hero Lab, there is about 10 students from Tokyo Tech working. I sometimes ask them some quiz for designing for educational purpose. And this time too, I asked them to find the good way to insert the rubber grip inside the pipe. But nobody proposed to use a glue. Okay, I think all the students, they are very good at making things, but nobody proposed. Maybe because they recognize glue as a glue. Glue cannot be a lubricant. Okay. So what is important to do some unconventional way of design or usage of the object is to think by the object itself, not by word. That's another thing I want to say. And another one is minimalism in robotics. This is not coined by myself. About 26 years ago, there was a workshop, minimalism in robot manipulator. And, it's not so popular. This word is not so popular. Well, to explain about this idea, I would like to introduce my latest experiment. Last July, the end of July, I have a chance to meet the president of TEPCO. And at that time, some worker in a nuclear reactor did not proper way of welding. When make a pipe welding, you have to fill the pipe with argon gas. But the worker, it seems, didn't do that. So internal surface of the welding part is not proper. And he wanted to find out a good robot system to do the inspection. I myself, in Tokyo Tech, I myself developed many pipeline inspection robots. These are old one. This one is done by Hybot, another venture company we made. This one has a zigzag-shaped body and expanded, well, it shrink by the spring and to produce propulsive force. It works very well, but afterward I made it. The user said it have to move the bending, bend one direction, bend another direction, out of the plane bending. Okay, and also it is compulsory to be able to pull out when something happened and stuck. But for this machine, it's very difficult to do that. Okay. Anyway, this is another model. Anyway, these are the robot what I made. There are so many elbows bending apart. So this conventional pipe is not useful. So we developed this model. It has no actuator, no sensors, no computer. Okay. By using a blower, airflow is supplied, and then the ball-shaped wheel is attached as interval, and so it goes into at the narrow hole with many elbows. And when you want to release it, all you have to do is to change the flow direction, and it works very well. And as for the reduction of the friction, it has a two-hemisphere wheel. That is very good to reduce the friction. If this part contacts the wall, it doesn't rotate. Okay. And well, I've been interested in this kind of wheel, and we talked with Dr. Tadakuma, who gave a plenary talk in this IROS. And when he was my student, we discussed, and he proposed to add a small wheel at the north and west pole. That's one solution. But I don't want to introduce a small mechanism. So what I did to just to offset, not in the middle, but a little offsetted place. So if it's offsetted and weight of the wires supplied, it's automatically adjust to this posture. And the inclined path, it's also lowering part is contact in the surface. Okay? It's a very simple way of solving the problem. And it has a camera here, and this one is a guide board, always aiming the camera to the direction of the pipe. So as you see, you can see the this one is a bad welding sample of the bad welding position, and it also has a iron board inside the transparent hemisphere cover. So if you see the position of the iron board, you know which direction is down. Gravity direction can be detected. And it works very well. This January, I got a letter of thanks from the TEPCO. And as it works very well, one of my the researcher decided to send a paper to the IROS, this IROS, but unfortunately it was rejected. I'm theoretical consideration is lacked. So optimal consideration should be done. So I agree this result, but I don't like one comment. It's written, it isn't clear that the robotics venue is the right place for this paper. There's no sensing, computation, or control that make up both the robot system. Okay. Well, I think, we shouldn't limit the robotics such a way. We should make it much more expanded position. So maybe we should establish a minimalism in robot session in IROS in future. Okay, so today, how to create a robot that contribute to society and science. 3 points: make fast, always making, and that expand the perspective, and also it's connected to scientific discoveries. And non-verbal thinking, always try to think by the object itself, not by name. Okay? Of course, computer simulation cannot be done by a word. So computation and machine design is very different, I feel. Anyway, this is very important for machine design. And minimalism in robotics. So the more you try to make the robot practical, it becomes minimalized, simplified. Finally, Hero Lab is recruiting lots of good robot researchers, engineers. Especially for the mechanical engineers, everything is getting AI or motor controls. So the field is getting narrower. But at least for decommissioning, I always take a special attention to make the mechanism with no motors, always make it mechanical drive system, which approach the high radiation area. So I think the one the geek, mechanics geek can enjoy decommissioning task. Thank you for attention.
Okay, thank you. Thank you, Professor Hirose. Great talk. You mentioned, Professor Hirose's work is rejected by IROS. Your paper is present here, so your work must be more excellent than Professor's, right? Okay. Is any question? This session I will not introduce this session. Fourth, we have each speaker has 35 minutes speech, and 5 or little longer Q&A, and we shift the next speaker after. We ask from floor to excellent researchers ask their question. Maybe even the two, it will be Mark Rabat and Professor Hirose will be different. The consideration. Then, but maybe last we have a few 10 minutes, something, maybe 20 minutes, depending how many questions from floor. Then we will close the session. Okay, and the question from the floor, we give about a couple of questions. So beautiful. Okay, please, you have one. Any question? If you have question, just go row there to stand at the microphone. Okay, then you have chance to ask questions. Okay, please go there. Just go my microphone. Go there directly.
Okay, thank you very much, Professor Shigeo Hirose Sensei. I'm Kenjiro Tadakuma, and I'd like to ask you so you suggest all of the audience to at first make the prototype more and more and to see the real phenomena, right? And to observe the real phenomena. But how to change the concept? I think you all often suggest the pivot to change the first concept, because the first concept is not the truly based on the real phenomena, right? Sometimes. So you suggest us that sort of things. In that case, you suggest us to think the pivot, right? Mm-hmm. So I would like to let you explain about when did you get such a kind of the way or method during your long time research or development term?
Okay, thank you for your question. I think I always describe that research and development is just like a mountain climbing. And when we start to climb the mountain, you can see high mountains. But if you climb the mountain, the view is changing. And once you make something, you have a little higher view. And so at that time, you can find a much better mountains. So, and if you see that mountain, of course, you keep climbing a higher place, you can get some height, but it's not optimal. It sometimes goes down and climb the other mountain top. So it happens quite often So I don't know how to do that, but while you are developing, you always try to have a wide perspective, not only walking to see the ground, to go a higher place, but always trying to look around, and you can find the new things. And then, if it's time to pivot, so you have to go down and start to climb another mountains.
But I think it's not so easy, right? So I'd like to know when did you get such a idea? It means for example, how old are you? Did you get that sort of quite brave idea?
If I can explain that, that's very good, but you always try to kind of thinking deeply, and also try to observe that activity from a kind of outsiders. So there's two persons watching. And for example, so when you're developing, I always swimming every day, and when I was swimming, that's very relaxing, and I can find maybe perspective view of what I'm doing. So, well, I don't know whether it's effective for everybody, but that's the only thing I can say.
Okay, thank you very much.
Okay, so move to next. I don't know who is first. Okay, okay, you got it. Okay, please.
First of all, thank you very much. It's always inspirational to listen to your talk, and you always see that you come years and years before people think that they found something. You did it already, but so thank you very much. The question I have is on these balls. You need a flow. You put a flow from the ensign. How many? Because of course you need a possibility to have pressure differences. Otherwise you couldn't have that motion. Have you been thinking also other propulsion where you can actually handle pipes which do not have this possibility?
Well, at least it has 30 meters wires, USB camera, and some boosters in the middle, and we get a very precise view. And if we put the ball wheel 1.5 meters the interval, but there should be some optimum design of the ratio of the diameter of the pulley and the diameter of the ball, and also the interval. These are not yet clear, so I want to clarify these points later.
Okay, thank you.
Yeah.
Okay, thank you. Just see. Maybe it is first. Okay, I'm pardon. Okay, you first. Okay. We will just give you three. Okay, give a chance to suggestion. Okay, after we answer. Okay, please. Okay, you go first.
Okay, so
yeah, you.
Shall I go first, or?
Yeah, you first.
Okay, so first of all, thank you very much for the excellent presentation. I was curious that about this trend in robotics that we put as many like expensive sensors on our robots as possible in order to get as much data for the environment at present, and such, for example, for like legged robots, we have some that have like 6 RGBD cameras all around them. And as far as I am aware, I wasn't the best at biology, but we humans only have 2 eyes and the front of our heads, not 6. And I was curious, this tendency in robotics to go with as many sensors as possible, would that potentially hurt like commercial applications in kind of the same way, create a gap between academia and industry as the sim to real gap? Shall we be investing more time in searching for more efficient ways to make robots work with fewer sensors? Or shall we first go the expensive way and then find a way to minimize it to kind of bridge the gap?
Well, it depends, especially in the decommissioning task. We should try to minimize the sensor. The sensor is very fragile, affected by the radiation. So, I feel people are not so seriously consider about the method with a device with no sensors. At least for the commissioning, it is under the teleoperation. It's okay to do the teleoperation. It's not. It doesn't necessarily be autonomous. So if some kind of signal is supplied to the human operator, we can do the teleoperation. So I think to make mechanically robust, minimum sensing method is okay, best. But of course, for other applications, we should consider about the sensor-based control method. So I don't deny this kind of research. People should approach many directions, and these will be helpful to handle the different applications. Okay.
Thank you very much.
Okay, right now it is your turn. Okay, please.
Thank you. And thank you for an amazing presentation. I very thoroughly appreciated every aspect of it. Thought I'd ask, in light of the venue and your most recent rejection, a more philosophical question, and I'd love to hear your definition of a robot and your definition of robotics, because there is some nuance and difference there, and getting your opinion there would be awesome.
That's extremely difficult. Since since robotic studies, many people start to define the robot, but it's always of no use. It's always changing. But at least if it's useful, and well, useful machine is engineering. We don't need to call it robotics engineering. But I think most of the engineering is divided, but the robotics engineering is the study of synthesized object. So we try to synthesize something to perform some task. I think we should call it robot, and we should gather such kind of research in IROS. That might be more fruitful and their application.
Okay.
Thank you.
Thank you. So you are last. Okay, please. Okay, you're waiting a long time, huh?
Thank you. I'm wondering, you've made so many different types of robots and mechanisms. How do you know when a robot is good enough to stop working on it?
Good enough. Well, at least it should be really used, and but I think I always say that we should have a lot of shelf to store the candidates of solving the problem. And if we study and store our head, or well, in the case of the laboratory, we try to educate the researcher, and all people know what kind of solution is suitable for a certain problem. So every time we try to classify the problem, and then if something new things happen, we can effectively use. So there's no limit of studying to solve the problem. Is it okay?
はい、ありがとうございました。
Okay.
Thank you both for your time. At the expense of biting the hand that feeds me, I suppose, I wanted to ask, at a very philosophical level, how do you feel about the institutions of science that we have currently with regards to both the conference format that we have, as well as maybe how information is disseminated to the public? Or I suppose I was curious over both of your experiences, which are very different. How do you believe that the modern scientific method and some modern scientific process is working? Like, are there ways that you would like to improve that? And maybe I'm just teeing up your institute very well here.
I could catch the question. It's about academia,
Yeah, about how do we as academics either improve how we do research or improve how do we communicate that with the public at large?
At least when in the case of the commissioning task, academia, although the information is open, but they don't get real problem. So there's some assumption they try to propose something, but it's not related to the real problems. So maybe we need some institute to connect academia and real world, not private company. So that direction what Hiro Laboratory is going to go.
Okay, thank you.
Thank you both for your talks. They're extremely interesting and really thought-provoking. One thing I've observed about robotics as a field is that not only are we like interdisciplinary, but we build on top of innovations from so many other, maybe more primary things. So the changes and trends in robotics, computing changes, technology, motor, actuator technology. What do you think have been the most impactful over your time working in robotics that have changed what's possible and what you're able to do? And what area would you like to see more development moving into the next 10, 20 years?
Okay, your turn. Okay, first.
At least for the hardware, very variable reduction ratio transmission might be extremely important. But until now, it's not yet proposed. So we have to use a harmonic drive or such kind of things. So if somebody made a good invention, that is a really good game changer. Of course, there's lots of things, but that's thing. But I just thought about.
Great, thank you so much.
Okay, thank you very much.
Thank you.